I am going to talk a little bit today about, as Hilda indicated, the urban context, but also the climate change context and their impact on the thermal performance and ventilation of residential buildings in my case. And we have chosen a case study. A residential building is Athens. I here have my co-authors, May Jun and Ted Ton from Brunel. May actually is now working at Sheffield University in the UK. And from Athens, in Lia Kristantoni and Dimitra Tsekanika, that they are from the municipality of Athens, and they are taking care of this pilot building. The results that I'm going to present, they are part of a European Horizon 2020 project, which is called Prelude, that includes 21 partners, and it is to be completed this November. You can see the website here. And we have 8 buildings as pilots in different European countries, in Denmark, Poland, Switzerland, Italy, and Greece, and also a testing living lab in Austria. Just a little bit about the project. It is about how we can get data from the buildings in different ways, because most of them, they are residential buildings, how we can simulate and how we can make sense of them, and then how we can use them so that we can increase the functionality in the space. And usually data and sensors are associated with high technology buildings, but in our case, we consider very much passive solutions, such as natural ventilation and cooling, and then predictive maintenance, and then big data and advanced analytic tools and proactive optimization where the technology is there. These are the buildings, just some photos of this, and the Athens building is here. They are all residences, apart from the building in Krakow, which is an office building. And again, within the project, there are quite a lot of things that they are happening, as you see. But there is a climate resilience work package, and within this one, we have been doing this study. So this study, as I mentioned before, is to look at the microclimate around a building and see how the external boundary conditions will impact on their thermal performance. So this is the building, and you can see the side streets in the building. You can see a typical floor plan, and you can see it's a kind of a hotel kind of building. But it has got long-term residents that they live for quite some time in there. And here you can see the environment around the building. It is a dense Athens urban environment, and we can see with the red our building here, that it is facing a very long street that starts from the center of Athens and moves to the outskirts. And the weather conditions, usually in simulations, we get them from the airport. So this is what it shows here, which actually shows that there are high temperatures in the summer. There are lower temperatures in winter that they might require heating. The wind direction is from the west, and here heating and cooling degree days, where you can see again that there is a need for cooling and there is a need for heating as well. Now, how we can model this building to take the surrounding areas into account, the urban context. So usually in simulations, what we do we have the geometrical model of our buildings, and this is how we usually do the simulations. Maybe we consider overshading of surrounding buildings, but this is it in most cases. But of course, the urban texture morphology is very important, and we need to calculate it and have some numbers that we can put in a software, and then they can show us the differences from the airport weather data. And usually these are in the forms of ratios, site coverage, facade to side, also the building height. And in our case, we used a software called the Urban Weather Generator. When we put all these numbers from the exact area around our building, it will give us the specific urban air temperature and the urban surface temperature as well. So temperature is taken care, but of course the wind is quite important, because in an urban environment, the wind will not be the same as in an open site. And in our case, the urban canyon with speed will be quite different, and we need to look at it by looking at what happens in the street next to our building in relation to other buildings around it. And finally, the solar obstructions of facade or overshadowing, as we sometimes call it, again, what the surrounding buildings will cut off from the solar access from our building. And when we do this, then we have a new weather file, which we can use in dynamic thermal and ventilation simulations. And the output that we can get, it will give us energy, ventilation, and thermal conditions demand in the urban context. I have put a paper here that has been authored, published some time ago, where all this that I try to explain in a few words, they are described in there. So for the urban weather generator calculators, then we need, I mentioned a couple of ratios before, but of course it is much more complicated. We need to compute quite a lot of different things. The question is how far we should go from our buildings. Usually 250 meters radius is what most researchers have been done. And then when we do all these calculations, I cut a slide. When we do all these calculations, we can put the information into the urban weather generation tool, and then we do our simulations, and then we get the results, and then we change our weather files. For the wind speed, then it is a little bit more difficult, and quite a lot of research is carried out at the moment because each situation is different. But for urban canyons, we were lucky that there were some work carried out some years ago, almost 20 years ago, under a European project called URBVent, where they have done quite a lot of measurements and then analysis, and then they have given us what equations, what algorithms we should use depending on the size of the canyon, the wind speed, and the wind directions. And also, I mean, the paper that I mentioned before, we have programmed this in the form of a spreadsheet that it is provided as an additional material. The solar obstruction is the easiest thing because it was calculated from the Energy Plus program that we use for the thermal simulations by just putting the buildings around the building that we are modeling. So I'm coming to some graphs. They are not results yet, but it is just the weather data comparison between the airport, the rural weather, and then what happens if we calculate the urban weather, what happens if we calculate the urban with the canyon wind. And also, in our case, we examine what will happen in the future. And for the future weather, we use the RCP 8.5 scenario for the year 2050. This is one of the worst scenarios, but the year is not very far away. So we are showing some results from that you can see again that the temperatures, they are going to increase. They are going to increase more in the summer. The wind here, you can see that there is not much difference between current and future, but there is quite a lot of difference between airport and whether we take into account the wind speed in the canyon, that you can see they are quite low wind speeds. So we carried out the simulations with rural weathers with no sundoes, rural weathers with overshadowing, urban weather files generated from the urban weather generator, and urban weather files with the urban weather generator and the urban canyon wind. And we did it for two levels of the building, a lower one and a higher one, to see the influence, what happens there. So some of the simulation results I am presenting here. Let's first focus what happens when we have rural weather and we have taken into account the shading for surrounding buildings. We can see that, as we saw even from the heating degree days, we need some heating and we need some cooling. When we go to the future, the heating is reduced, higher temperatures, and the cooling is increased, again because of the higher temperature. If we compare the lower floor with the higher floor, we can see that the heating needs are less, and this is in the winter because, again, of overshadowing. At higher floors, we have many more useful solar gains, while there is more shading in the ground floor. And we have got higher cooling demand. This is because we think because the wind speed is higher at higher loss, so we have got more losses due to infiltration and ventilation. And then when we are going to the future, then this becomes quite worse. When now we look at the shaded with urban weather, we can see that if we look here and here, we can see again urban weather, urban heat island, higher temperatures, so less heating is needed in winter, but much more cooling is needed in the summer. And in the future, it will be much worse. Probably the heating need is very low. And if we look at the upper floors, the heating need is really low, and mainly we have got the need for cooling. And finally, if we take into account the wind, that it will be less in this canyon, especially for lower floors, and then the infiltration and ventilation will be much reduced. We can see that in the future, in the lower floor, the same result, but it is more pronounced. So we need to take this into account where our building is within the urban heat island to design for today, but what will happen into the future to design for the years that the building will last. And the same is true for refurbishment of buildings as well. If now we look at heating demand at the higher floor, this is monthly, and this is telling us the same thing in a different way. We have in January, which is the coldest month, some heat in demand. If we add shading, it becomes higher. If we add shaded and urban weather, it comes down, the same as if we use the airport weather. But if we use the urban canyon as well, is coming lower, and this is true for all the months. If we look now at the cooling demand, for the current weather, and again for the higher floor, we can see again in August, for example, we've got this demand for the simple simulation. Overshadowing, it's less because more shading. Taking into account the urban heat island, then higher temperatures and shading, so we go back to square one. And if we take into account the wind, so we've got a slight increase of the demand as well. Looking now at a building, or the same, our case study building, what happens if there was no air condition in the building? And we looked at the percentage of summer hours that they are overheated, calculating them from the summer period, June to September. And the percentage of summer hours within the adaptive comfort temperature range for a category 2 building. So we can see here that we've got quite a lot of hours that they are red, which means no thermal comfort for the buildings. And if we take for the occupants, and if we take the urban weather into account, then this becomes worse, and with wind a little bit worse. In future weather, it becomes quite impossible, really. Only a little bit less than 20% is comfortable, and the rest of the time is uncomfortable. And this is for a west-facing room, and we looked at an east-facing room that we can see here that in the future, in 2050, in 25 years, then there is no way that we can provide thermal comfort using natural means for this building. So a straightforward simulation will tell us that we will be comfortable half of the time, but when we consider the other parameters, it tells us, even in current situation, that we will be comfortable much less hours. And I think that this is towards the end of my presentation, where I'm trying to summarize that the confounding effects of urban density, urban textures, and exposure to the wind, building design and human activities alter the weather characteristics over and around the urban areas, that sometimes we call it the microclimate around our building. So we generated these weather files using the urban weather generator and also included urban canyon wind calculations, and we compare the different weather impacts on the building thermal performance. Also consider overshadowing for a case study building which is in Athens. So what we observed from the simulation is that we have an increase of the cooling demand by 24%, and in the future it will be 66%. The total energy demand, heating and cooling, is increased only 3% for the lower floors, but 12% for the higher floors because of the reduction in the heating demand, as we saw. But in the future, this increase will be higher, 13% against the 3% for lower floors and 32% against the 12% for higher floors. And if the building is free floating without air conditioning, an adaptive thermal comfort analysis indicated that only 25% of the summertime will be comfortable in the future, in comparison to 50% with the current typical weather file. So the conclusion is that the use of a suitable weather file to include urban external conditions in thermal simulations is essential for more accurate prediction of energy demand and the internal avoidance of overheating in buildings without air conditioning. And with these conclusions, I would like to thank you very much for your attention. And I will introduce the next speaker, who is Adam O'Donovan, who is going to start his presentation after me.